Good day, I'm J Wildberger, and today we're going to look at the algorithm of finding the square root of a number. This is an important operation that goes back to antiquity, to the ancient Greeks, to the Chinese, to the Arabs, the Babylonians even, and to the Hindus. It's important because it's the basis for solving quadratic equations. Without being able to take a square root, the quadratic formula doesn't make too much sense. And let's start off with an example and show you three different approaches to the subject. The one that we're mainly interested in is one developed by the Hindu mathematicians, and it's a very practical algorithm that you can try yourself after you've learned it. Alright, so here's an example. 523 squared equals this number, 273,529. We say that 523 is the square root of this number. And the idea is we are given this number to start with and we're trying to find the square root. Well, one way of approaching it, which is a good way for public school students to start thinking about the subject, is to make some guesses. 500 squared is 250,000, while 600 squared is 360,000. So the real answer must lie somewhere in between those two guesses. And then we can make some further guesses, keep on squaring the guesses that we have, seeing if we're getting bigger or less than our starting number. And eventually we would zero in on our number 523. Here's another method that goes back to the ancient Babylonians. Basically the idea is this. Suppose that x squared equals n is the equation we're trying to solve. So what we do is we make an initial guess x1. We compute n divided by x1. Then we set x2 to be the average of these two numbers, the average of x1 and n divided by x1. And then we repeat the process using x2 instead of x1. So the idea is that if x1 is exactly the square root, then n divided by x1 will be equal to x1, and these two numbers will be equal. Otherwise, one of them will be less than and one of them will be bigger than the square root. And so averaging those two numbers is a relatively good guess for the square root. And if we keep doing that, then we approach the square root value. This method is essentially the same as Newton's method, discovered by Isaac Newton, which is taught in calculus courses. And without going into too much detail, the idea is roughly that we have a curve and we want to find its zero. Say the curve is represented by the equation x squared minus n. Then what we do is we take one guess here and find a tangent, see where that tangent intersects the x-axis, and then that's our next guess, and then the next tangent gives us the next guess, and so on. So it turns out that this Babylonian method, 4,000 years ago, is essentially Newton's method in this particular case. However, for pen and paper calculations, or even by computer, it's a little bit slow in the sense that you have to rely on dividing and repeated divisions. So let's have a look at the third method, which is due to the Hindus. So this Vedic method relies on the following identity, that x plus y squared is x squared plus, we can write the rest in this form, 2x plus y times y. So the basic idea is that we're going to have an initial approximation, and then we're going to guess how much we have to adjust that initial approximation by computing a term like this. So in our example, we're 523 squared. Let's make the following observations. 500 squared is 250,000. Okay, so that's less than our number n. 520 squared will be, according to this law here, it's 500 squared plus 2 times 500 plus 20, so 1,000 plus 20, times 20. It's a way of thinking of how you go from here to here. What you're doing is you're adding this new component. And that turns out to be this number here. Then the next stage, 523, all squared. Well, that's what we have at the previous stage. That's 520 squared right there, plus something extra, the extra term given by 2 times 520 plus 3 times 3. So this is a clue to how to set up the Vedic algorithm. And here's how it works. We write down the number that we're trying to find the square root of, and we divide it into groups of 2. We look at the leftmost group of 2 and we find its square root, which is a number between 0 and 9. In this case 27, its closest square root is 5. 5 squared is 25, and if we subtract 25 from here, the 2 comes down. And then we also bring down the next pair of numbers, so now we have 235. This corresponds to our initial guess of 500 squared. Okay, now in the next step what we have to do is we are going to multiply what we have up here, the 5, by 2. 5 times 2 is 10. And we're going to leave a little space for an extra digit. That's like the y. And we're going to try to find an extra digit here, in this case 2, which has the property that this digit times 10 with a digit is pretty close to our remainder 235. So we're looking for a digit, number between 0 and 9, so that when you add it to 10, 1, 0 times a digit, and multiply it by the digit y, then you're getting something that's close but less than 234. So if we tried 1, for example, we would have 101 times 1. Well, that would be less than 235. But 2 also works. 102 times 2 is 204, which is less than 235. 3, however, would be too big, because 103 times 3 would be bigger than 235. So 2 is the right number, and we subtract 204 and we get 31. Then we pull the 29 down, and then we're going to repeat the same process with 329. So what we do is we take 52, which we've already got, we multiply it by 2, there's 104, and we add room for an extra digit. And now we have to choose that digit so that when we multiply the digit times this number, we get something that's less than or equal to our remainder. And it turns out that 3 exactly works, and when we subtract, we get a remainder of 0, telling us that 523 is the square root of our original number. Let's have a look at another example. Alright, so here's the number that we're trying to find the square root of. We write that number down and we group its digits into groups of 2. Looking at the leftmost group, its square root, or closest to it, will be 7. 7 squared is 49. We subtract and we get 2. Then we pull down the next pair of digits for a remainder of 263. And now we're going to take the 7 multiplied by 2 for 14 and trying to find the new digit, y, so that y times 14y is close to 263 but less than it. Well, 1 is the best one, because if we use 2, we get 142 times 2. That would be bigger than this. So we put a 1 there, we put a 1 there. 1 times 141 is 141. We subtract. We get 122, and then we pull down the 85. Now at this stage we have 71 already. Multiply 71 by 2 right there. Now we have to guess what the new digit is, so that this times this is less than our remainder. Well, you have to adjust, but there's only possibilities from 1 to 9, so it's not that bad. You guess 8, and 8 works. 8 times this is this number here. Take the subtraction, and you get 861. And finally, we pull down the last pair of numbers, 96. Take 718, multiply it by 2 right there, and leave a space. Find a digit 6 in this case, so that 6 times this number with a 6 there is less than or equal to our number, our remainder. And that works out exactly, so we get 0, meaning we've got an exact square root. The answer is 7186. Next time we're going to have a look at how algebra helps us understand patterns generated by special numbers. I hope you'll join me for that. I'm J Wildberger. Thanks for listening.